For the given problem, you have to find the equivalent system model, that is equivalent mass and stiffness of the given system. The system is a pulley damper type of arrangement. In this, there are two pulleys. So let's draw this. This is the inside pulley, which is pinned. The radius of this pulley is R. There is an outside pulley with the radius 2R, and this pulley is connected to a damper which is represented by the damping coefficient C, and this pulley will turn theta angular displacement in radians, and there's a mass which is hanging on an inextensible string. The mass is of m kgs. The linear displacement of this mass is going to be in x. This mass is connected to the ground with the help of a spring of stiffness k. In this problem, you have to find the equivalent stiffness, and mass MEQ, and equivalent stiffness you want to find. So the kinetic energy of the system and the potential energy of the system will help us find the equivalent mass and stiffness. Let's first find the relationship between the different coordinates that are available. So we have already marked theta as the angular displacement of the pulley, x as the linear displacement of the mass m, and let's say y is the displacement of the damper piston damper arrangement. So let's find the relationship between each of these. So theta can be written as equals to x by r. Okay, from simple geometry you can find this. Y is equals to 2r, so 2r is the radius of this bigger pulley, times theta, so that then r theta can be written as x, so this will be equals to 2x. Now so let's find out the T, which is the kinetic energy of the system. So you know that kinetic energy is translational plus rotational. So the translational energy of this mass is half mv square, or half m. V can be written as x dot, so half mx dot square, plus the rotational energy of this pulley. Pulley will have a moment of inertia of I. So the rotation energy is half I and theta dot square. Okay. So then you can now replace this theta dot with x dot using the relationship between theta and x. So this equation will become half mx dot square plus half I x dot over r whole square. Finally you can write this as equals to half m plus I by r x dot square. So in the bracket whatever you see, that is m plus I by r square, this will give us the equivalent mass of the system. So let's say this is MEQ. Okay. Similarly, we have to find the potential energy of the system. The potential energy will be stored in the spring. And there's only one spring in the system. So you can easily write down the potential energy V equals to half kx square. Okay. Now that is the potential energy of the system. Now we can also find the equivalent um, damping of this system. Okay, so in order to find that, we have to first find the work done in the system. So work done from state 1 to 2 can be written as equals to C y dot dy, okay, integral from x1 to x2, okay, from state 1 to state 2. This is the cy dot times dy. Okay, so how we have come up with this equation? Very simple. Force is proportional, the damping force is proportional to the velocity. So velocity, let's say, is y dot. So if you remove this proportionality sign, you can come up with cy dot. Okay, so the force times the displacement, that is dy, will give us the work done from state 1 to state 2. Why there is a minus sign over here? Well, the negative sign indicates that the work is lost, or in the damping the heat is dissipated, so that's why you have got a negative sign. So let's write this y coordinate in the x form now. So let's look at this. Will become integral x1 to x2, c times y dot will be equals to 2x dot, okay, and then dy you can write as equals to d of 2x. So finally you will get this as equals to negative of x1 to x2 for cx dot dx. Okay, so this is the final equation for work done. So this is work done 1 to 2. Okay, and this portion over here will give us the equivalent damping. So you have got the equivalent mass, you have got the equivalent stiffness, and we have got the equivalent damping. So this is the solution for the problem. Thank you.